A mass on the end of the spring causes the spring to oscillate up and down. Kinetic energy, potential energy. If we graph the height of the spring, we get something that looks very interesting. It looks like a wave, up and down, up and down, up and down. A pendulum swinging back and forth, back and forth, back and forth. A string being shaken, going up and down, up and down. What do all these things have in common? All of these systems have particles which are oscillating. To oscillate basically means to move back and forth in a rhythm, in a rhythmic motion with a pattern. Keep your eyes on just one of these green particles of the string. You can see that it's very simply just going up and down, up and down, up and down. The pendulum from earlier was swinging back and forth, back and forth. The spring was bobbing up and down, up and down, up and down in a rhythmic patterned way. All of these things are united in the fact that they have oscillations, they have oscillatory motion, and they can all be described using the single phenomenon of waves. First of all, let's get a definition. What is a wave? You saw the pendulum swinging, you saw the spring bouncing, you saw the string being wiggled back and forth, up and down. What do all those things have in common? Energy and particles oscillating, moving back and forth. So when we go to try to define a wave, we need to include both those ideas. We have energy, and then we have particles that are oscillating, that are moving back and forth in a rhythmic patterned way. So maybe we can define a wave like this: energy traveling through a substance known as the medium, causing the particles of that substance to oscillate, or we could say vibrate, with a pattern or a rhythm. That's what I'm going to say is a pretty good definition of a wave. Does that definition apply to the pendulum? Does the pendulum have some sort of rhythmic wave-like motion? Well, I think so. We know there's energy in the system. Right now, this pendulum is elevated off the ground. So hopefully you remember that the type of energy it has now could be called gravitational potential. And we know that as soon as I let it go, it's going to be swinging, it's going to be moving, and so it's going to have some amounts of kinetic energy. And that energy is oscillating back and forth between potential and kinetic as the pendulum swings up and down, back and forth, as the pendulum itself oscillates. So this does kind of fit our definition of a wave. How about the string from earlier? Does that fit the definition? Do we have energy in this system? The system being the string itself. Yeah, we do. It's moving. It has kinetic energy. Is that energy causing the particles of the system to oscillate, to vibrate, to move back and forth in a patterned or rhythmic way? Well, yeah. Once again, keep your eye on the green dot. It is moving up and down, up and down, up and down. Energy is moving through the system. We might use the word propagating. Energy is propagating from left to right through the system. It all starts here with this little machine. And that's causing the particles to oscillate. So that's the definition, basically, of a wave. Energy traveling through a substance, known as the medium, causing the particles to oscillate. And this whole unit is going to be all about waves and their different applications, how they relate to sound, how they relate to light, how they relate to those magic rectangles that none of you can ever put down, your phones, your smartphones, and how those receive information, data, and how the modern world uses that to communicate. All of these things described by the phenomenon of a wave. Are there different types of waves? Yes, there are several different types. The two main types, as you'll see here, are electromagnetic and mechanical. Electromagnetic waves we will talk about at the end of this unit, but I wanted to just throw the definition out there for you right now. This is a fancy word for light, electromagnetic waves or electromagnetic radiation. This is almost, you can think about it like pure energy. And this type of wave is interesting because it does not require a medium. It's actually capable of traveling through empty space. Electromagnetic radiation, or light, turns out has the properties of a wave. Another way of defining an electromagnetic wave or light is that it's the oscillation of the electromagnetic field That's complicated. We'll get there. We'll talk about that at the end of the unit. What I'm going to focus on today are mechanical waves. Mechanical waves, that word mechanical in physics is a fancy word that basically means stuff that can move around, matter that can move. So mechanical waves are formed from energy traveling through a medium. It does require a substance through which to travel, unlike light up here. Mechanical waves are matter being wiggled around by energy. That's kind of the basic definition of a mechanical wave. Matter being wiggled around due to energy passing through. The energy propagates through the matter, and the particles of that matter, the particles of that medium, oscillate or vibrate. And there are two types of mechanical waves that you should know about, longitudinal and transverse. This is a longitudinal wave. What observations can you make about it? Well, let's look at two things. First of all, is there energy passing through? Yeah, if you look over here on the left side, I have something that's kind of moving back and forth with a rhythmic motion. That's adding kinetic energy to my system, and that energy is passing through the system from left to right. So yes, I have energy propagating or passing through the system. And that's causing the particles of the system, all these little dots, to do what? To oscillate, to vibrate, to move back and forth. Well, can we be more specific? Can we describe how they're oscillating? Yeah, they're oscillating. Keep your eye on the red dot. They're oscillating from left to right, back and forth, left to right. Left, right, left, right. It's patterned, it's rhythmic. That's an oscillation. The particles are oscillating left to right, and the wave energy itself is moving left to right. If you kind of zoom out, take a step back, and look at the system as a whole, you'll see these places where all the particles are kind of shoved close together, traveling from left to right. The places where the particles are spread far apart, traveling from left to right. So because the particles are oscillating from left to right, and the wave energy itself is propagating left to right, we can classify this kind of wave as a longitudinal wave. So the definition of a longitudinal wave energy propagating left to right, the particles vibrate left to right. In other words, the particles oscillate parallel to the wave motion, left and right. That's a longitudinal wave. Here's another little image of it. You can see that the wave energy is traveling from left to right, and the particles are oscillating left and right, back and forth. So they're parallel, they're in the same direction. That's longitudinal. This wave, however, is different. First of all, does this fit the classification, the definition of a wave? Well, yeah, there's clearly energy passing through. There's a change happening to this substance. That, by the way, was our definition of energy way back in our energy unit. Change, or the ability to cause a change. So my system is changing, it's moving. And you can see that the energy of movement is kind of traveling from left to right through the substance. You can see that it's kind of wiggling around from left to right. The energy of the wave is propagating from left to right. But keep your eye on a single particle. How are the particles moving? How are they vibrating and oscillating? Up and down. So the wave energy is traveling horizontally, left to right, and yet the particles are oscillating up and down. That's perpendicular, right? 90 degrees away from each other. That type of wave is known as a transverse wave. So we have two types of waves. Longitudinal, that's when the propagation and the oscillation are parallel. Transverse is when the particles are oscillating in a direction that's perpendicular to the wave motion. In other words, the wave energy propagates left to right, and the particles vibrate up and down. This is longitudinal. This is transverse. And they are both classified as mechanical waves because it requires matter, particles, substances through which the energy passes.